a very nice lineup of talks. The first one is by Ryan Sanders, but he has actually pre-recorded it because he couldn't make this time live. So I'm going to try to play this, and if you have any questions for Ryan afterwards, just put them in the Slack, and hopefully we'll get Ryan to check in and answer them later. So put them, again, underneath the talk, underneath Ryan's talk in the Slack under session 2B. Similarly with the questions for other people, just write them into the Slack, and we will, I'll read them out at the end, as many as I can get through. Okay, so with no further ado, I will try to share my screen and play Ryan's video here. Okay, so let us go to full screen. And here is Ryan Sanders from UC Davis.
I'm a postdoc at UC Davis. I'd first like to thank the organizers of SAZERAC for allowing me to pre-record this talk since I couldn't make the time live. Today I'd like to talk to you about the metallicities and ionization properties of galaxies in the epoch of Reionization, and in particular what we can learn from extreme galaxies at redshift 2 that are analogs of galaxies at redshift greater than 6, and future prospects for measuring metallicity with synergies between James Webb and ALMA. This work has been done in collaboration with the MOSDEF survey team shown on the left, and in particular with Alice Shapley at UCLA, and also with the group of collaborators that I've listed in the lower right of this slide, in particular with Tucker Jones at UC Davis. The James Webb Space Telescope will soon provide us with rest-optical spectra of galaxies at redshift greater than 6 for the first time. And a big question is, what will we do with the measurements made from these first James Webb spectra? From the NIRSPEC, NIRCam, GRISM, and NIRIS instruments, James Webb will measure the H-alpha and nitrogen 2 emission lines to redshift 6.6, oxygen 3 and H-beta to redshift 9, and oxygen 2 and neon 3 to redshift 12. Some major science objectives for measurements of these emission lines include characterizing the chemical abundances and chemical evolution of galaxies at the highest redshift, the ionization state of star-forming regions, and the properties of massive stars in these early galaxies. And in particular, the last one has connections to the ability of star-forming galaxies to reionize the universe. The tools that we'll use to extract this information from measurements of the emission lines include strong line metallicity calibrations that convert line ratios into gas phase metallicities, and modeling of the emission line spectra using photoionization codes. Now, even at redshift of 1 to 2, the ionized gas conditions in H2 regions are different than they are in the local universe, requiring different metallicity calibrations and a different set of assumptions for modeling redshift 2 emission line spectra. And we expect that the situation is possibly even more different for typical galaxies at redshift of 6. Therefore, in order to maximize the science return on the first wave of James Webb observations, we need to answer two questions. The first is, what metallicity calibrations are appropriate for use at redshift greater than 6? And the second is, what is the proper set of assumptions for photoionization modeling of emission spectra from redshift greater than 6 galaxies? I'm going to address these questions using a sample of about 20 galaxies at redshift 2 with direct method gas phase metallicities. These direct method metallicities are very robust and are derived from the electron temperature based on detections of weak auroral emission lines such as oxygen 4363 in the rest-optical and oxygen 31663 doublet in the rest-UV. I've shown some examples of detections of these weak emission lines for galaxies at redshift 2 on this slide. Now, why this sample at redshift 2 should be able to inform our knowledge of galaxies at redshift greater than 6. Here I've shown on the left specific star formation rate, and on the right equivalent width of O3 plus H beta, both as a function of stellar mass. The redshift 2 direct method sample shown in red here has much higher specific star formation rates and emission line equivalent widths on average than typical redshift 2 galaxies shown in blue on these slides, and much higher of course than redshift 0, which is shown in the gray. And in particular, if I put up on these slides some determinations of specific star formation rate and H beta plus O3 equivalent width at redshift 7 based on broadband photometry, we see that this direct method sample at redshift 2 is actually comprised of very good analogs of UV bright galaxies in the epoch of reionization. Let's first take a look at the metallicity calibrations. In these plots, I'm showing on the left the R23 line ratio and on the right the O32 line ratio as a function of direct method metallicity. The redshift 2 auroral line direct method sample is shown in red, and the median of this extreme redshift 2 sample is shown in the black diamond. Now I'm comparing to some other samples here. In the black line we have redshift 0 H2 regions, in pink we have typical redshift 0 galaxies, and in green line, we show local analogs of high redshift galaxies. This is from work from Beyond et al. 2018, these high redshift analog calibrations. And what we find is that typical redshift 0 galaxies and local redshift 0 H2 regions do not produce calibrations that can reproduce the metallicities of the extreme redshift 2 sample. But local analogs of high redshift galaxies, again shown in the green line, appears to reproduce the average properties of the extreme redshift 2 sample quite well. And so the conclusion here is that local analogs of high redshift galaxies can produce accurate metallicity calibrations that can be used for galaxies at redshift of greater than 6. We should not use typical redshift 0 metallicity calibrations. A caveat here is that we haven't confirmed this for nitrogen-based indicators, only for indicators that are ratios of oxygen, neon, and hydrogen lines. We performed photoionization modeling of the extreme redshift 2 sample to place constraints on the ionization parameter and the shape of the ionizing spectrum. Here, the shape of the ionizing spectrum is parameterized in the stellar metallicity, which traces the iron abundance. And in particular, because we have the direct method metallicities, we can fix the nebular metallicity in the photoionization models, allowing us to get non-degenerate solutions for ionization parameter and the shape of the ionizing spectrum. The results are shown here. In the left panel, we show ionization parameter versus nebular metallicity. And what we find is that the extreme Z of 2 sample is not offset from the local relation between ionization parameter and nebular metallicity. On the right, we show stellar metallicity, which again traces iron abundance, versus nebular metallicity, which traces the oxygen abundance. And what we find is that the stellar metallicity is lower on average than the nebular metallicity. And this indicates that these galaxies have supersolar oxygen to iron abundance ratios, which drives hard ionizing spectra because iron poor stars are hotter and thus produce harder spectra. Now, this supersolar oxygen to iron abundance ratio is expected for galaxies that have rapid formation timescales and high specific star formation rates because oxygen comes from type 2 core collapse supernovae and is thus produced on a short timescale of approximately 10 megayears, while iron comes predominantly from type 1a supernovae, which are delayed, and the enrichment of iron happens on a timescale of approximately a gigayear. So our suggestions for modeling redshift greater than 6 emission spectra are to assume the local relation between ionization parameter and nebular metallicity, while assuming that the stellar metallicity, that is the iron abundance, is approximately 1/5 the value of the nebular metallicity, which traces the oxygen abundance. This value of 1/5 is approximately the limit for pure type 2 supernovae enrichment. Now, it's very useful to draw conclusions from these analogs of galaxies in the epoch of reionization, but ultimately we'd like to test these inferences by measuring direct method metallicities of galaxies at the highest redshifts. But the truth is that even with James Webb, it's not going to be feasible to detect oxygen 34363 for galaxies of redshift greater than 6. Even at low metallicities and high electron temperatures, this line is still about 50 times fainter than oxygen 3 5007. And so we need an alternative and more accessible method to derive the electron temperature in the epoch of reionization. To this end, we've developed a new method to measure direct method metallicities using measurements of the oxygen 3 infrared lines at 52 microns and 88 microns from ALMA in combination with rest-optical lines from JWST. This method is very similar to the traditional method that uses oxygen 4363 to get the electron temperature, but in this case the electron temperature is derived from oxygen 352 microns or 88 microns. And for these UV bright redshift of 7 sources, you could get the ALMA line, the infrared lines with ALMA in approximately 10 hours per target, and the optical lines with James Webb in a few hours per target. Now, we don't have rest-optical emission line measurements for galaxies at redshift greater than 6 at the present time, of course, since we don't yet have James Webb. So what we've done is instead inferred the H-beta luminosity from the UV star formation rate for galaxies at redshift 8. We have assumed fiducial values for the electron temperature and the electron density, as well as the ionization correction factor. All of these assumptions equate to approximately a 0.4 dex systematic uncertainty in over H, but basically what you see in this equation at the bottom of the slide is that we can determine the oxygen abundance from a combination of the 88 micron oxygen 3 line that's been measured by ALMA for several redshift 8 sources and the UV star formation rate. I'll say very briefly that we have tested this 88 micron method under our set of fiducial assumptions on a sample of redshift 0 low metallicity dwarf galaxies and find that it recovers the metallicities inferred from the traditional method using oxygen 3 4363 quite nicely with a nice 1-to-1 relation. The 1 sigma scatter is 0.2 dex. Here I'm showing the results of applying this new method to a sample of 5 redshift 8 galaxies with measurements of the O3 88 micron line from ALMA. For these UV bright galaxies of redshift 8, we find a typical metallicity of about 10 to 20% solar at 10 to the 9 solar masses. This represents an evolution of 0.5 to 0.9 dex lower in metallicity at fixed stellar mass compared to the redshift 0 mass metallicity relation. And this is a similar typical metallicity to the redshift 2 extreme sample that I was using earlier as analogs. These metallicities are low but not extremely low, which carries important implications about the star formation histories of these galaxies. The future prospects of using synergy between ALMA and James Webb to study chemical evolution at redshift greater than 6 are very exciting. To conclude, I'll go ahead and put up a summary slide that encapsulates some of the main points of the talk. I apologize I won't be able to answer questions live during the conference, but I put my email address in the upper right corner of this slide, and I'd be happy to discuss via email if anyone has any questions. Thanks for listening.